First, I want to thank the organization gave me the opportunity to present our research work here. Second, now I want to thank all the attendance to this meeting. Today I want to talk about the novel treatment of engineered human H2 decoy peptide to SARS-CoV-2 and its variants-induced acute lung injury. The current SARS-CoV-2 pandemic has killed over 60 million people in the world and 1 million people in America alone. Although mRNA COVID-19 has shown impressive efficacy against this virus, however, emerging of multiple variants of SARS-CoV-2 has challenged the current vaccine efficacy. SARS-CoV-2 variants saw variable escape from vaccine immunity. The COVID-19 vaccine was developed based on SARS-CoV-2 strain isolated from Wuhan patient. The SARS-CoV-2 variants isolated from UK and South Africa show some escape. Brazilian variants show more escape with more mutations. When the escape is below the threshold, new vaccine are needed. Therefore, besides the vaccine development, it's imperative to study the mechanism of SARS-CoV-2 infection and provide novel and efficient treatment to this deadly disease. There are currently a few therapeutic approaches focused on blocking SARS-CoV-2 binding to its key receptor, SAE2, the most advanced cocktail of the neutralized antibody. However, SARS-CoV-2 spike protein might develop accumulating mutation to escape the selection pressure. Therefore, other approaches are also intensively studied, including soluble recombinant human H2 decoy peptide. The soluble recombinant human H2 are currently being under different stages of development against COVID-19. So from here, you can see the green part is the spike protein of the virus. The red part is the human H2 receptor. So for monoclonal antibody, spike protein specific antibody blocking spike protein and prevent viral fusion. For engineered SAE2 decoy, SAE mutants are engineered to binding spike protein more tightly than native SAE2, which inhibit SARS-CoV-2 infection in vitro. So our objective is to engineer SAE2 derivatives with affinity as a rival monoclonal antibody. From here, a library of SAE2 variants was selected by flow cytometry for increased binding to receptor binding domain of the SARS-CoV-2, the green part. So the library, the mutant human H2 is linked to the red color. So if you from flow cytometry, we can select the high green part. So cell displaying SAE2 mutants with high binding, a green gate, were collected and deep sequenced to exhaustively determine which mutation were enriched. So SAE2 mutation in the blue are enriched in the selection for the spike protein. Enriched mutations tend to cluster a small number of the hotspots with the SAE2 spike interface. So we did a binding affinity experiment. So from here, you can see for the the dotted line is the SAE2 wild type. The solid line is our decoy peptide. The black color is SAE in the monomerical form. The gray color is dimeric SAE2 IgG1. The binding protein detected by flow cytometry in human cell line express spike protein from original strain. So the figure A shows that both monomerical and dimerical decoy peptide had a better binding affinity than SAE2 wild type. Compared to wild type is green color, and the dotted line and the solid line is our decoy peptide. So we further did all the variants of the concern. Our decoy peptides show much higher binding affinity to these variants of concerns. we conclude SE2 decoy peptide binding spike protein from highly transmissible variants. If you from here, you can see the figure B is UK strain, figure C is from South Africa beta, figure D is gamma from isolated from Brazilian, figure E is delta from Indian, and figure F is a strain isolated from California. We also did for the current Omicron BA.1, BA.2, the variants of concern. You can see to compare this binding dimerical human S2 AGG protein to compare binding to all this monoclonal antibody authorized for the therapeutic used in the clinic. You can see our decoy peptide, the blue color, is much better compared to wild type and all this monoclonal antibody. The current monoclonal antibody already lost their therapeutic effect for the Omicron. Next, we want to test the prophylactic therapeutic treatment for this prophylactic effect of our decoy peptide. So we give one-time delivery human S2 our decoy peptide 12 hours ahead of SARS-CoV-2 infection. You can see one-time delivery completely block virus infection. The mouse body weight kept going up compared to without this treatment, the mouse body weight lost the body weight. Also, we did Evans blue figure C is Evans blue and Burin assay is the assay to test the lung vascular permeability. You can see virus for the control on the day 7, the virus, the mice have a severe permeability leakage. Our decoy peptide have no permeability problem. For the therapeutic effect of the human S decoy peptide, this is our experiment design. We have 3 groups. We have group 1 as a control, group 2, group 3. Sorry, we give this our decoy peptide 1 as a start point at 12-hour post SARS-CoV-2 infection. The third one is a 24-hour post SARS-CoV-2 inoculation. We give once a day for 7 days. We test for WA strain isolated from Washington State. It's most close to the original strain isolated from Wuhan. So we also you test for strain P.1. P.1 is much more laxic strain than WA strain. So from here, this is for WA strain. You can see we have a 2 treatment group, 1 start from 12 hours, 1 start from 24 hours. You can see the figure A, both of the treatment start point all have half of mice survived. So figure B is Evans blue and Burin assay. You can see the first column without Evans blue injection, the second column with the Evans blue injection. The first row is baseline without any virus inoculation. The rest of 3 is on day 7 post inoculation SARS-CoV-2. You can see the first group is PBS. The third row and fourth row are 2 treatment group. If you see the figure C, both of treatment group, the lung permeability was reduced, including there are no big difference compared to long wet dry ratio. So this is the pulmonary edema is not significant difference. So this is a P.1 strain, is a gamma strain. You can see only treatment group start from 12 hours. The mice have half a mice survived. The treatment start 24 hours. The just life extended, but still all died on day A. So we can see the pulmonary, also the decoy peptide protect the lung, mouse lung from permeability from the virus injury. Also, for 12 hours, the pulmonary edema is much better. So the question comes, why the human H2 decoy peptide significantly? So why this our decoy peptide for the WA strain, they can have a therapeutic effect for both of the 12-hour and 24-hour. However, for P.1 strain, only starting from 12 hours works. So we did virus replication, the qPCR to test the viral load on different group on the day 7. So for the WA strain, we collect them on day 7. It's the most time point for the injury. For the for the P.1 strain, we collect them on day 6 because P.1 strain is a much toxic virus, so the mice all died on day 6. So compared to here, you can see on the day 7 PBS group, control group, P.1 have a much higher viral load, replication ability compared to WA strain. Therefore, we think the treatment is kind of a compete, is timing compete. For the WA strain, start from 24 hours is still okay, but for the high replicate virus like a P.1, so the treatment have to start early to block the virus binding and the replication. So I come to another question. So because ACE2 activity, they have a different mechanism have a physical rule in the cell. So we think ACE2 activity that offers second potential mechanism of action for the treatment of the COVID. This is the physiological role of the ACE2, the receptor for SARS-CoV-2. You can see so ACE1, so the from the angiotensin to the ACE1 can convert angiotensin to angiotensin 1, angiotensin 2. So ACE2 can further convert angiotensin 1 to angiotensin 1 to 7, angiotensin 1 to 9. So this is have a protection to the vasodilation, anti-fibrotic, anti-inflammation effect. So the question comes, so does the conversion of angiotensin 2 directly address COVID-19 symptoms? So to answer this question, we generated catalytic dead. We call it soluble SAE2 2.4 NN. So this NN removes the collectrin-like dimerization domain and it contains natural site for proteolytic processing. The catalytic activity assay showed that the catalytic dead lost the cleavage function. The binding affinity assay and B for activity and C for dead show no change for affinity for the receptor binding domain of the SARS-CoV-2. You can see the binding affinity no change. However, the catalytic dead lost the catalytic activity. We did the same experiment design. After SARS-CoV-2 inoculation, we give virus 24 hours and start once a day for 7 days. We have 3 treatment groups. The group 1 is IgG as a control. We also have group 2 is catalytic active is our decoy peptide. The third one, the green color one, is the catalytic dead human H2. From here, you could probably survivor. You can see the catalytic active, the mice, over the half of mice survive. However, the catalytic dead, most of the mice died. So from this part, we can conclude the catalytic activity of the engineered IgG is critical to therapeutic efficacy. Conclusion. So prophylactic soluble SE2 decoy peptide prevents SARS-CoV-2 entry and acute lung vascular injury. The treatment of the decoy peptide improves the survival of a SARS-CoV-2 WA or P.1 strain infection, alleviated lung vascular injury, and facilitated lung vascular repair. The catalytic activity of engineered decoy soluble SE2 is critical for the mild survival of the SARS-CoV-2 infection. I would like to thank all these people. It's a collaboration with different professors. Dr. Eric Prock is the one generating this decoy peptide in the UIUC. Also, I would like thanks to Dr. Malik, Dr. Roman, Dr. Limberland. So thanks to all the funding and the university. I would like to take any questions.